All right, well, good morning again. Thank you again to Dalhousie for having me. I wish I could be there in person to talk with you about hurricanes. Hope everyone is staying safe and healthy there. We're going to be talking about the Atlantic Basin Seasonal Hurricane Forecast for 2020, basically how we go about doing these seasonal forecasts, and I'll spend a little bit of time talking about hurricane categorizations as well today. Some research that we've recently been doing, talking about the current Saffir-Simpson hurricane wind scale, and maybe some things we could do to make it a little bit better. And I think especially for those living in Atlantic provinces of Canada, I think it's a little more relevant than just simply looking at the maximum wind speed. So to begin with, whenever I do any presentations about seasonal hurricane forecasting, I always like to begin by acknowledging Dr. Bill Gray, who was the founder of the seasonal hurricane forecast. In addition to founding the seasonal forecast, he made fundamental contributions to tropical cyclone structure, intensity change, genesis, and he was just an all-around great guy, great mentor to me for over 15 years. And so certainly we wouldn't be doing these seasonal forecasts if it weren't for the great research that he did. Our group has been doing seasonal hurricane forecasts all the way since 1984. If you're interested in more on Bill Gray, you can review a paper that we published a couple of years ago highlighting his research legacy. But Dr. Gray was a big fan of philosophy, and he really liked one of the greatest philosophers of all time, the Yankee catcher Yogi Berra, who once stated that it's tough to make predictions, especially about the future. And certainly whether you're trying to forecast the outcome of a sporting event or you're trying to forecast weather and climate patterns, certainly it is tough to make forecasts. But there is another statement by Yogi Berra that I think really kind of helps catalyze basically the methodology that we use, and that is that you can see a lot by looking. So basically the way that these seasonal forecasts got started back in the early 1980s was Dr. Gray noted that when you had El Nino conditions, that is warmer than normal water in the central and eastern tropical Pacific, you tend to get fewer hurricanes in the Atlantic Ocean. And what this does is it gives you an overall view of basically gives you a empirical relationship where El Nino means fewer hurricanes in the Atlantic. But then the question is trying to understand the physics of how something going on in the tropical Pacific Ocean would impact hurricanes in the Atlantic. So that's what we do, is we basically find these kind of statistical relationships and then try to understand the physics as to how these relationships develop. And I think that's one of the reasons why it's important to develop these types of statistical models, is that it teaches you a lot about the atmosphere and the ocean and how they interact and behave, because obviously with hurricanes, it's a very tightly atmosphere-ocean coupled process. And so if hurricane seasons were completely random, and you were to say, look at the 10 most active hurricane seasons since 1950 and difference them from the 10 least active seasons since 1950, we would expect that there would be very little, you wouldn't see any coherent spatial patterns. But obviously, if you look at this map, you can see there's a lot of coherent spatial variability that exists. And so with hurricane seasons, we know the data pretty well back to about 1950. As you go back further in time, there's more uncertainty in the hurricane observations. As I'm sure all of you know, it also gives more uncertainties with the oceanic as well as the atmospheric observations. But back to 1950, the data is reasonably good. So here we can see that when you have active hurricane seasons, different from quiet seasons, this really kind of brings out the largest signals you can find. And you can see, as you would expect, more active Atlantic hurricane seasons are associated with warmer water in the tropical and North Atlantic. Makes sense since hurricanes live off of warm ocean water. More warm ocean water means more fuel for those developing cyclones. But it also tends to be associated with lower pressure, more moisture, all of these conditions that tend to be associated with more active seasons. If you look in the tropical Pacific, you can see a good signature for La Nina events. La Nina is associated with a stronger Walker circulation that shifted westward. So when you have a La Nina event, what that tends to do is it tends to reduce the upper level westerly winds in the Atlantic that typically shear apart the hurricanes. And you can see it in this schematic here. When you have an El Nino event, you tend to get a little bit stronger low-level winds, low-level trades, but much stronger upper-level westerly winds that really ramp up the vertical wind shear, which tears apart the hurricanes as they're trying to develop and to intensify. And the El Nino signal is really strong, especially in the Caribbean, into what's known as the western part of the main development region, so going back to about 40, 50 degrees west. As you move farther east in the Atlantic, the El Nino signal is somewhat weaker. Alternatively, when you have a La Nina event, you get much weaker upper level westerly winds, so you get overall much weaker vertical wind shear. I should point out, in the Atlantic, we have a vertical wind shear that's typically there because your low level winds are the trade winds out of the east, and your upper level winds are out of the west. So typically you have a shear. El Nino increases that shear, La Nina decreases it. And we use a lot of these other historical relationships, and I'll be talking about some of the relationships that really go into our forecast as I break down the forecast here in the next few minutes. So we did put out our forecast a little less than 2 weeks ago. With the forecast, we're calling for an above normal hurricane season in 2020. The average Atlantic hurricane season has about 12 named storms. Of those 12, 6 becoming hurricanes, and of those 6, 3 becoming major Category 3, 4, and 5 hurricanes. Those are hurricanes with winds of 111 miles per hour or greater. This year we're calling for a total of 16 named storms. Of those 16, 8 becoming hurricanes, and of those 8, 4 becoming major Category 3, 4, 5 hurricanes. We also use several integrated metrics. One of the ones that we talk about a lot and you may have heard of is this accumulated cyclone energy metric. Basically, it's an integrated metric that takes into account the frequency, the intensity, and the duration of storms. So a storm like Hurricane Dorian last year or Hurricane Irma generates a tremendous amount of ACE because they're very long-lived, very intense hurricanes, whereas a short-lived storm like Barry or Olga or Pablo last year that was out there for just a couple of days generates very little ACE. And so that kind of gives us one kind of integrated metric that we really like to use to verify overall seasonal hurricane activity levels. So we're forecasting about 140% of the average Atlantic hurricane season in 2020. So we use a total of 3 predictors that are kind of underpin our seasonal forecast from a statistical modeling perspective. And what we use here is we use high resolution sea surface temperature data from the NOAA Optimum Interpolation product, as well as we use the recently released ERA5 reanalysis. That reanalysis goes back to 79. The high resolution sea surface temperature data goes back to 1982. So we use the data since 1982 to develop our statistical model. And so one of the things obviously that we want to be very careful of when we do these statistical models is that we aren't overfitting the data. So note we use a total of 3 predictors. We also want to make sure we have pretty good solid physical underpinnings for why these predictors would work. And we also use a cross-validation approach whereby we leave the year out of the model that we're trying to forecast. It kind of gives you basically kind of a high-end idea of how much skill the model should have in real time. One of the challenges is that, of course, the climate is always changing. We obviously know we have anthropogenic changes, we have natural variability. So that's one of the reasons if you look at the seasonal forecast from CSU, they've changed with time. As the data gets better, as the climate changes, the predictors that work may change somewhat. And I'll talk a little bit about that here in a few minutes as well. So these 3 predictors in combination, if you go back to 1982, we verify again off of this accumulated cyclone energy, that integrated metric. If you look at the figure here, you can see that the model does a reasonably good job. So as you probably know, the Atlantic hurricane season starts on June the 1st, but it really doesn't ramp up until August. About 95% of all your major hurricanes occur after the 1st of August historically. So we're still quite a ways away from when the season really ramps up, which is about 4 months from now. But you can see reasonably good skill. In cross-validated mode, a correlation of 0.65. Certainly not perfect. There's certainly years where the forecast busts, like 2003. 2003 we were too low. 2013 the model was too high. But overall you do see a reasonably good coherence between what the model is predicting and what we got for observations. And we have some new techniques that we're using. One of the new ones that we've been working on is using a statistical dynamical model. And one of the reasons we can do that now is because climate models have obviously come a long way. When Bill Gray started doing these forecasts in 1984, they were extremely primitive, and obviously now they're running at a much higher resolution, and they have a lot higher levels of skill. And so our best statistical model, as you would expect, is the one that we issue on the 1st of August, which is again right prior to when the season really ramps up. Now obviously I would love to know what July conditions look like that go into my August model now. We don't know that, but what we can do is we can use a climate model to forecast what overall conditions are going to be like during the peak of during the month of July. Our statistical model did call for a pretty active season, a little bit even more than what we're predicting with our final seasonal forecast. So our statistical dynamical model uses a total of 3 predictors. What the model again does is it forecasts July large-scale conditions, and then we use the historical relationship between those July large-scale conditions and what goes on during the peak of the season to then come out with our final output. So these three predictors in combination we've shown do really well in our statistical model, and the dynamical model does a surprisingly good job, even for March, of predicting what the large scale is going to look like during the month of July. Now, you can't say obviously what the winds are going to look like, say, on July 18th, but when you do a monthly average, these models do have some skill. So in this case, we're using two different models. I'll start by talking about the European Center model, the SEAS 5 climate model. We're also this year for the first time using the Met Office model. So these three predictors in combination we have then applied to a simple linear regression scheme, doing again cross-validation. You get a correlation of 0.6, which is slightly lower than what we got from the original statistical scheme. But when you look at those three predictors in combination, it is very bullish on the hurricane season, calling for even more activity than what we predicted. So this model is very aggressive at calling for an active hurricane season in 2020. If you combine the statistical model and statistical dynamical model, basically just do a simple average of the two, you get even a higher level of skill, and that makes sense. We've seen this a lot in a lot of different atmospheric and oceanic forecasts, that when you use an ensemble of forecasts, the skill improves even more. As I mentioned before, we're not only just using the European Center model, we're now also incorporating in the UK Met Office model, which is the Glossy 5 model. So the UK Met Office, unfortunately the hindcasts from the European Center go back to 1981, so we can test the model on over 30 years of historical data. The Glossy 5 hindcasts, unfortunately, are at a shorter time scale. They run from 93 to 2016, which is a little bit short for developing a statistical model. When you have to do regressions on only 23, 24 years of data, that makes it a little bit more challenging. But if you look simply at the correlation between what the Glossy 5 model and the European Center, the SEAS 5 model, forecast how the correlations are for the predictions of the July 10-meter wind, which is probably our predictor that has the most skill. You can see that the Glossy 5 during this 24-year time period has even higher correlations than the European Center. And it happens at all 5 months where we look at the model skill from March through July. So again, this gives us confidence that Glossy 5 is a useful additional model to add. And the Glossy 5 model is a little bit lower, but still calling for a well above average hurricane season in 2020. And so consequently, all of our different statistical and statistical dynamical model guidance is pointing in the same direction, which gives us a little bit of increased confidence that it's likely to be an above normal hurricane season in 2020. Obviously, we do want to point out this is early April. A whole lot can change between April and the peak of the season. I'll talk a little bit about some of the large-scale factors that we're looking at in just a couple of minutes. We also use analogs, and basically the way that we use analogs is we go back into the past and we look for years in the past that had conditions most similar to what we currently see, but really more similar to what we expect to see during the peak of the Atlantic hurricane season. And so in this, we usually try to pick out 5 different analog seasons, so 5 years in the past that look most similar to what we currently see. And there's obviously a lot of uncertainty with exactly what is going to occur during the peak of the season, so we try to kind of accommodate several different types of scenarios. So in this case, in 2020, we think the odds of El Nino are pretty low, and I'll talk a little more about that in a minute. But we don't really quite know what the Atlantic is going to look like. The Atlantic right now is generally warmer than normal, but just because it's warmer than normal now doesn't guarantee it's going to be warmer than normal during the peak of the season. So what we do here is we try to predict. We pick years that we think are not going to have don't have El Nino conditions, but have various different Atlantic sea surface temperature configurations. And so our 5 years that we picked, 4 out of the 5 years, if you look at ACE, generally ACE above 100 is above normal. 4 out of the 5 years had above normal hurricane activity. 1960 was a little bit below normal. And you can see the average of the 5 analogs is fairly close to what we're actually ended up forecasting for the 2020 overall hurricane season. Again, one thing I do want to point out with these forecasts is that we give you our best estimate, but obviously there is some uncertainty associated with those. And so that's what we've really tried to focus on during this past off season, was a little better way of quantifying the uncertainty of our statistical and our statistical dynamical models. And so we present now our probability of exceedance plots. So basically these are the probabilities of exceeding a particular value, in this case ACE. An ACE of 100, again, is about an average hurricane season. So the blue line here represents the climatology, so effectively what percentage of seasons historically have had an ACE of at least 100. And the red line represents the forecast for 2020, whereby we basically have fit historical ACE to a Weibull distribution. And then what we do is you basically shift the mean of that distribution to what you're, instead of 100, say, you're shifting it over to 150, which is our current forecast. And then what we do is we basically use instead of saying the standard deviation, basically we use a normalized distribution. So you're saying the standard deviation, if there were no skill, is 1, and we adjust that down because our model does have some skill. So consequently, what we're trying to do is basically kind of give it some error bars. When you look at a number, you say, okay, the ACE is 150, but what is kind of your confidence interval? And so NOAA gives about a 70% confidence interval, which if you look at a probability of exceedance plot, it would be between the 15th percentile and the 85th percentile, will give you 70% of your forecast should fall within that range. So there's our 70% confidence interval for ACE. We did a similar exercise for all the different predictors in our scheme. And so here's the uncertainty range, and this is kind of similar to what you see when NOAA does their forecast. They'll give a range of 6 to 10 hurricanes, say, and so that's our range currently based on the skill of the April forecast. So as we get closer to the season and the model's skill gets better, you will see these ranges somewhat shrink. So the means obviously will be whatever the mean is, but the range around that mean should be somewhat smaller because the forecasts have higher skill, and therefore your uncertainty range should shrink somewhat. One of the reasons that we like to do the midpoint of the forecast is I think that helps to generally focus the public's attention on kind of your best estimate. I've seen a lot of times when, say, NOAA does a forecast of 6 to 10 hurricanes, the media will say up to 10 hurricanes, and then people take that to mean that you're forecasting 10 hurricanes. So we like to provide it in both ways, but really focus on the midpoint for our particular outlooks. So when it comes to the large scale, here's what we're looking at for 2020. Here's a map of current sea surface temperature anomalies. And so the blue box highlights the ENSO region, so El Nino, La Nina. And the red box is kind of the main development region for where Atlantic hurricanes typically develop and intensify. And just a couple of things I wanted to point out. If you look at this figure, you can see a lot of warmth. This is a 1988 to 2017 climatology, so some of that is just, climate change warming. One thing I do want to point out is that the Gulf of Mexico might jump out as a hot spot, and certainly it is. It's very warm there right now, 3 to 4 degrees Celsius warmer than normal. The far North Atlantic is quite cold right now. There's been a lot of discussion. I'm sure you're pretty familiar with a lot of the research that's been talking about potentially a weakening of the meridional overturning circulation of the ocean with the really warm anomalies off of the east coast of the U.S. and cold anomalies farther north. I'll talk a little bit about that. And then we're going to talk about the tropical Pacific Ocean, where you can see right now we've had basically warm neutral ENSO conditions, so not quite up to the El Nino threshold, but water's running between about 0 to half a degree Celsius warmer than normal. And so one of the big questions, of course, is an El Nino going to come on? Are we going to lose those conditions? I think the odds of El Nino are pretty low, and I'll talk a little bit about that here in just a minute. So one of the things that we look at whenever we're talking about El Nino is, what are the low-level wind conditions looking like? When you get low-level westerly winds, that tends to force downwelling oceanic Kelvin waves, which tend to reinforce warmth in the eastern and central tropical Pacific. In this case, right now, if you look, this figure is a Hofmöller, basically along the equator. And so what I look at is for westerly winds near the international dateline. When those are present, it tends to reinforce warmth. And so we had a little bit of a westerly wind burst recently, but we didn't see much of a downwelling Kelvin wave associated with it. The upper ocean heat content has really translated downward over the last few weeks, and I think the odds of even warm neutral ENSO conditions are pretty low. I tend to think we may even head towards La Nina by the peak of the hurricane season. You can see this is a forecast from the Climate Forecast System, the U.S. government model from NOAA, mostly calling for weaker or stronger trade winds near the international dateline as indicated by the blue colors, which I think should help promote continued anomalous cooling in the eastern and central tropical Pacific over the next few weeks. The latest forecast from NOAA, they do probabilistic forecasts for August through October. There's about a 50% chance of neutral conditions for the peak of the hurricane season, about a 30% chance of La Nina conditions, and just a little over 20% chance of El Nino conditions. So climatologically, your odds of El Nino during August through October are about 30%. This year it's a little bit lower than normal, and I think those odds of El Nino are even a little bit lower than that, just given kind of the current setup of the ocean, as well as the wind forecasts that are coming up. But as I'm sure most of you know, there is what's known as El Nino predictability barrier during the Northern Hemisphere spring. Climatologically, your trades are fairly weak right now. The oceanic thermocline is more predisposed to kind of rather large changes this time of year. So unfortunately, ENSO forecasts have fairly low predictability during the time when we really need them to have high predictability because we're doing our seasonal forecast. So that's one of the challenges with the seasonal forecast, and that's one reason why our seasonal forecast skill improves considerably by June and especially by August, because you're through that El Nino predictability barrier time of year. As I'm sure a lot of you know, there's a whole lot of models forecasting El Nino. There's a bunch of dynamical models, some statistical models. So anything above the red line at 0.5 degrees Celsius is generally what NOAA defines as El Nino. Below minus 0.5 is La Nina. If you look at this figure here, you can see most of the models are calling for near normal water conditions. So between El Nino and La Nina, meaning neutral ENSO conditions. There are a few that are pretty aggressive at calling for La Nina, and a couple are hanging on to El Nino. But overall, I think the best estimate is neutral conditions, potentially headed more towards weak La Nina conditions, especially as we head into September and October. The Atlantic is running generally pretty warm right now. Most of the tropical Atlantic is warmer than normal. You see again those cold anomalies in the far North Atlantic, and you really see it as really very warm anomalies in the Gulf of Mexico. And so there's been a lot of discussion with all that warmth in the Gulf of Mexico. Does that mean we're going to see a more active hurricane season in the Gulf of Mexico? And fortunately, that doesn't necessarily follow. And the reason why that's the case is because, as you know, the Gulf of Mexico is extremely warm every year. So water temperatures are not kind of the limiting condition in that region. Normally what limits hurricanes from developing and intensifying in the Gulf of Mexico is too much shear, sometimes there's too much dry air. You also need an organized disturbance in the Gulf of Mexico to get the storm to develop and to intensify. So if you look at a map, you have correlations between Gulf of Mexico water temperatures and Gulf of Mexico ACE or Gulf of Mexico hurricanes. The correlation is basically zero, and that's the primary reason is because it's not sea surface temperatures that are the limiting factor there. Similarly, if you go to the western North Pacific and look at correlations there between the number of, say, typhoons or ACE in the western North Pacific and sea surface temperatures, the correlation is actually slightly negative, and that's because the waters there are plenty warm to support hurricane activity in any year. It's other factors that are much more important. Whereas in the Atlantic, water temperatures, especially in the eastern part of the basin, are a little more marginal, so you need them to be warmer if you want an active season. It also is much more closely tied to the overall environment in the deep tropics, where you have warm water, you have low pressure, you have reduced shear. Those tend to go part and parcel together in the Atlantic basin. So overall, the current sea surface temperature pattern that we see does tend to match up pretty well with what I'm going to show you next, which is a correlation map between ACE in the Atlantic and sea surface temperatures. So in this plot, basically what it's showing is where you have oranges and reds. That indicates where warm water leads to more active hurricane seasons. You don't really see very much in the way of blue because, in general, if you want the Atlantic to be active, you don't want cold water in the Atlantic. But you can see kind of where the focus is, and it's mostly focused in the eastern Atlantic, which if you step back and look at this figure, you do have quite a bit of warmth in the eastern Atlantic. Currently, we see that, and warmth seems to actually be building, or the anomalous warmth seems to have actually built a little more over the last couple of weeks. There's a lot of models that forecast a large scale. This is the forecast from the Climate Forecast System model, recent forecast from them. It's very bullish at going straight to La Nina. The Climate Forecast System does have some biases, I think, that tend to make it go to La Nina a little more often than it should. But if this forecast were to verify, it would be a very active Atlantic season with a moderate La Nina in the Atlantic, moderate La Nina in the Pacific, combined with the warm sea surface temperatures in the Atlantic and in the Caribbean, likely leading to a very active overall hurricane season. So, unfortunately, one of the things that obviously everyone would love to know is, when is a hurricane going to make landfall? Are the hurricanes going to make landfall? Because that's obviously a huge question is, if there's a bunch of hurricanes in the Atlantic Ocean, it doesn't really necessarily matter if they're not making landfall. And unfortunately, as you probably know, we can't forecast landfalls at a seasonal timescale. Those are governed by day-to-day weather events. You can forecast the overall hurricane activity for a season because it responds very well to the large-scale environment, which has some predictability. But trying to predict where storms are going to go is dictated a lot by mid-latitude weather patterns, which don't have that nice long-term predictability. But what we can say is that in general, more active seasons have more landfalling hurricanes. If you look at, say, the 10 most active Atlantic hurricane seasons since 1950, compare them with the 10 least active seasons since 1950, and look at the number of landfalls, certainly many more landfalls in the active hurricane seasons. So what we do is we calculate probabilities of landfall. And the numbers here on the right-hand side in parentheses, these are the climatological probabilities, so the long-term average probabilities for each part of the U.S. coastline as well as the Caribbean of being impacted by a major Category 3 to 5 hurricane, winds of 96 knots or greater. And the numbers on the left are the probabilities for this year, which again are elevated because we're predicting an above normal hurricane season. Now we emphasize with all of our forecasts that you need to be prepared the same every year because it just takes one hurricane making landfall near you to make it an active season. But again, if you look long term, more active seasons do tend to have more landfalling hurricanes. So we have probabilities for these large regions, and we also have probabilities for individual states from Texas to Maine. Here are just a few examples. And these are hurricane impact probabilities, and the reason that impacts is slightly different from landfalls is because in general when a hurricane makes landfall, it doesn't so in one state. Obviously you can have hurricanes that make multiple landfalls where they make landfall in an area, then track into another ocean, and then make a second landfall. You often see that, say, with a hurricane like Andrew, where it made landfall in Florida, then tracked over to the Gulf of Mexico and made a second landfall in Louisiana. But in general, hurricanes make landfall in one state, whereas hurricanes may impact several states. So in this case, the definition of impact is sustained hurricane force winds. The National Hurricane Center has a database for every hurricane back to 1851, where it made landfall, but also which states it estimates had sustained hurricane force winds. So these probabilities are based off of that. So in the case of Florida, you've got about a 50-50 chance climatologically of being impacted by a hurricane, and about a 1 in 5 chance of being impacted by a major hurricane. This year it's 68% for hurricane, 31% for major, again because we're forecasting an above normal overall Atlantic hurricane season. As I mentioned briefly before, our forecasts are updated. We do our first forecast on the 2nd of April, which then is updated on the 4th of June, an additional update on the 7th of July, and a final update on the 6th of August. Again, these forecasts tend to have improved levels of skill as we get closer to the peak of the season because we're closer to the events that we're trying to predict. If you really can't get enough of seasonal forecasts, we have a website, seasonalhurricanepredictions.org. On this website, we have about 25 different groups submitting predictions. And so this range from government agencies like NOAA and the UK Met Office to private sector weather companies like the Weather Company, Weather Bell, and Weather Tiger, and universities like ourselves at CSU, Penn State, NC State, etc. And so if you really want to see what's going on in terms of what each group is doing for seasonal forecasts, I invite you to check out this website. We have gotten some contributions already for 2020. This list will continue to grow in the next few weeks. Here's basically a screenshot that I grabbed earlier today. There's 7 groups that have submitted their forecasts to our website so far. All of these groups are calling for an above normal hurricane season. You can see the average of these forecasts is denoted by the orange dot, which is 8. The red dot is the number of hurricanes to date. We haven't obviously had any hurricanes yet in 2020. That number will rise, obviously, as the hurricane season gets going. But again, all of these groups are calling for an above normal hurricane season so far for the 2020. And so now I wanted to shift gears a little bit and look about a question that's been asked that I think was an important one to ask, and that is, what predicts hurricane damage better? Is it the wind or is it the pressure? And so the reason that kind of got motivated to do this study was because there's been a lot of pushback about the Saffir-Simpson hurricane wind scale in recent years, and a lot of people saying, don't pay attention to the scale, it's not particularly relevant, it doesn't describe the damage or necessarily the risk. And so what I said was, well, when it comes to hurricanes, we measure 2 things and every time the Hurricane Center puts out an advisory, it provides 2 pieces of information. Provides the wind and also provides the pressure. And having grown up on the east coast of the United States in Massachusetts, I found that they've downgraded a lot of the hurricanes that were formerly Category 3s. When they've done the reanalysis, the pressures have stayed low, but they've knocked down the winds, so the hurricanes aren't as categorized as highly anymore. And some of these storms are very impactful. And we find, especially as hurricanes move up along the east coast of the U.S. and into the Atlantic provinces of Canada, their winds may come down, but the storms tend to grow in size. They get larger as they move farther north, so the pressure tends to stay low, and we can have very significant impacts from these storms. And so just to give you a case in point, these are two storms actually making landfall in the Gulf of Mexico. We have Hurricane Charlie, which was a Category 4 hurricane, very impactful near the Port Charlotte, Punta Gorda area in 2004. It was a Category 4 hurricane. And then we had Hurricane Katrina in 2005, which was a Category 3. And so both of these storms are very impactful, but in terms of the area that was impacted, the area impacted was much higher for Katrina than it was for Charlie. And if you look at Charlie, it had the stronger maximum winds, but obviously Katrina was a much larger storm, about 3 times the size of Charlie, and the surge from Katrina was much higher. So obviously, we saw, obviously the big story with Katrina ended up being all the people that perished in New Orleans, but even had the levees held, several hundred people in Mississippi died due to Hurricane Katrina from the storm surge, 28 feet of storm surge. And so there was a lot of consternation when Hurricane Katrina, after the season, was categorized as a Category 3, and people said, how could a storm that caused that much damage and had that much surge been categorized as a Category 3? But if you look at the pressure was extremely low with Katrina, over 20 millibars, 20 hectopascals lower than it was with Charlie. And so a couple of pieces of motivation for this research is that pressure is just easier to measure. It's much easier to measure with an aircraft than is wind, because if you think about a hurricane, the winds are in a swath, so you're trying to measure the strongest winds in a large scale area. Whereas the pressure, if you fly through the hurricane, you can drop a sonde in the eye, you can measure the pressure quite accurately, whereas wind is much harder to measure, and it's certainly much harder to measure sustained hurricane force winds on land. Anemometers chronically fail in high wind conditions. It's just very, very hard to measure that elusive, what's defined by the Hurricane Center as a 10-meter open exposure. Once a hurricane makes landfall, that really doesn't exist anymore. So trying to measure that wind is much harder. Whereas the barometer, it doesn't even have to be outside. You can measure the pressure as it goes along. You can get really good measurements of the pressure. And overall, the pressure has been shown to be a more robust metric of overall storm intensity. I think part of the reason why that's the case is because it's more of an integrated metric, because the pressure, hurricanes obviously live off of the pressure, or the winds from the hurricane are obviously derived from the pressure. But you also have to think about if you have a very, very low pressure in the center of the storm, but the winds aren't that strong, that typically means you have a pressure gradient spread out over a large area, so it means you have a very large storm. So it's more akin to this integrated kinetic energy metric. That's one of the ones that the Hurricane Center talks about these days. And there was a paper back in 2016 that said, hey, we find pressure works better than wind in terms of predicting damage, but they just very briefly touched on it. And so I thought it would be good to go and look at this in a lot more detail. And so what I'm going to start with is just showing you, this is from our paper that was should be coming out in the bulletin of the AMS in the next few weeks, showing the relationship between wind and damage from 2007 to 2018. You can see where there's been a lot of pushback against the Saffir-Simpson scale. Here we're plotting ranks because we don't want to have it all dominated by, say, 1 or 2 storms like Sandy. And so if you plot the damage where you rank the storms by damage, higher damage meaning giving a higher rank. Likewise for wind, higher rank means stronger wind. The correlation is 0.29, which is pretty anemic. It wouldn't even be statistically significant. You can see, I guess there's a little bit of an upward trend, but it's really hard to do much with that. Whereas if you do the same for pressure, it's not a perfect fit, but that's a pretty good fit. Correlation of 0.9 almost for these 12 years. And so that's gives us some justification for this type of analysis, but of course you could say, well, it's 15 storms. You can get high correlations on 15 storms with various metrics. So let's look and see how well does it work in a much larger data set. So what we did next is we looked at hurricane damage going back to 1900. And obviously damage in 1900 was a lot less than it is now, simply just due to inflation, but also you have to take into account both the population has skyrocketed during that time, along the coast, as well as we have more stuff. We're wealthier than our parents and grandparents were. So what we do is a normalized damage approach. And so if you look at the normalized damage, so again, taking the damage these storms caused when they made landfall and adjusting them to how much damage they would do if they were to make landfall today, and you plot them versus wind, you can see there's a pretty good relationship there, a correlation of 0.66. But if you look at it with pressure, it's even better, a correlation of 0.77. That difference is significant at the 5% level because you have a lot of data points. We're looking at 165 different landfalls going back to 1900. So that gives us some kind of motivation for looking at pressure as a more robust metric than for wind when you look at these storms over a long period, so 119 years of hurricanes. When we find that the relationship for the Gulf Coast is pretty well equal, whether you use pressure or wind. We argue let's use pressure because it's easier to measure, but the correlation is just marginally better. Whereas for Georgia to Maine landfalls, you see a much better relationship for pressure than you do for wind. The correlation between damage and wind for Georgia to Maine landfalls is only 0.42. When you look at it with pressure, the correlation jumps to 0.81. So very similar correlations using pressure for the Gulf Coast or the East Coast. Whereas for wind, you really don't get much relationship along the east coast of the U.S. Again, I think it's largely due to the fact that these storms tend to grow in size as they're starting to become more post-tropical, extratropical. So you do get a pretty good fit. And I think one thing that's interesting to point out is that, we can get a correlation if you step back. The correlation of 0.77 gives you almost 60% of the variance explained for damage just by knowing what the pressure is at landfall, not even saying where the storm made landfall, because obviously a storm making landfall in a densely populated area, all else being equal, is going to cause a lot more damage than a storm making landfall in a more sparsely populated area. So what we said next is let's actually take the winds from the Saffir-Simpson scale and let's add a pressure categorization to it. On the right-hand side in this table is what was originally listed in the Saffir-Simpson scale for pressure. So the Saffir-Simpson scale was originally designed by Herb Saffir, and all it had was wind and damage. Then Bob Simpson added the pressure and the storm surge. Well, the storm surge didn't always go with the wind speed, so they removed the storm surge component, but at the same time they removed the pressure component. And we're recommending re-adding the pressure component back into the Saffir-Simpson scale and making that the primary metric that we use to categorize hurricanes. And so the way that we assigned pressure to those various categories is we did basically look at the lifetime maximum intensities that hurricanes tend to have. So basically, for example, in this figure, Category 1 hurricanes, about half of all named storms in the Atlantic reach Category 1 strength. About half of all named storms in the Atlantic have a pressure of 990 millibars or below. So consequently, that's how we assign that category. And we did that all the way up to Category 5. It's about 20% of all of all named storms reach major hurricane strength. About 20% of all named storms have a pressure below 960. Likewise, Category 5, it's about 3% to hit Category 5. About 3% of all 3% of all named storms have a pressure below 925 millibars. Fits in pretty well with what was originally defined by Bob Simpson in his analysis. So if we do this, what we find is that we can actually recategorize hurricanes using the pressure. And if we do this, we do end up with more upgrades of hurricanes than downgrades of hurricanes, and especially along the East Coast, a lot of upgrades from category from category 1s and 2s to major hurricanes. Some of the most notable ones, obviously Katrina, getting upgraded from a Category 3 to a Category 5 because its pressure was below 925 millibars. Sandy from a Category 1 to a Category 4. I do want to note, of course, Sandy was post-tropical officially when it made landfall, but it was still categorized as a hurricane several hours before it made landfall. And had it been categorized as a 4 as opposed to a 1, I think it might have gotten people's attention a little bit. And we know with Sandy, it had a very high storm surge associated with it. It also obviously made landfall near climatological high tide with both, so we had that issue as well. But Sandy was certainly a very, very impactful storm. But you can see the various upgrades and downgrades along the coast. Again, because we've certainly seen some of these hurricanes with much lower pressures than what the winds would have driven. But again, you see most of the upgrades along the east coast of the United States, especially from Georgia to Maine. Just again, to briefly talk a little more about Hurricane Katrina. Again, it was a Category 3 by wind, a Category 5 by pressure. You can see it's a very large storm on satellite imagery. And the storm surge inundation from Katrina was really quite remarkable, up to 28 feet in portions of the Mississippi coastline. So again, even had the levees held in New Orleans, and we hadn't seen the epic flooding there, we still would have had several hundred fatalities just from the storm surge in Mississippi. And then finally, kind of one of the things obviously that's most important is, you can replace stuff, but you can't obviously replace human life. And so if you look at the relationship between wind and fatalities, here we go back to 1988. And the reason we only go back to the mid-80s is because we're trying to compare with storms that had reasonably similar kind of warning structures. Obviously, if you go back really far, we just didn't predict the storms as well, so more people lost their lives simply because we didn't have the warning systems that we have now. But if you look at the relationship between wind and damage, or wind and fatalities back to 1988, correlation is 0.33, so relatively weak. If you look at the correlation for pressure, certainly not perfect, but you're getting quite a bit more of the variability if you have the pressure. So we argue that it's a good idea to be using pressure in the future to categorize hurricanes as opposed to wind. I think especially along the east coast of the United States, and certainly I would say it would also hold true for these both hurricanes as well as cyclones becoming post-tropical as they head towards the Atlantic provinces of Canada. So with that, I'd like to thank you very much for your attention, and I like to always finish my presentations with an admonition from Arago, who was the head of the Paris Observatory in the mid-19th century, who stated that never, no matter what may be the progress of science, will honest scientific men or women who have regard for their reputations venture to predict the weather. And so with that, I'd like to thank you very much for your attention. Here's my contact info, and now I'll look and see if there's any questions. So I don't see any questions as of yet. Feel free to ask. I'll hang on here for a couple more minutes to see if anyone has any questions. All right, I see a question coming through. Yeah, that's a good question so Eric has asked a question, and the question is, how do integrated seasonal metrics correlate with impactfulness metrics? And so, when you look at these impacts, so you look at impacts from hurricanes, these larger storms do tend to have higher levels of impacts. If you look at basically, instead of correlating, what I did is I developed a seasonal ACE metric based on pressure as opposed to wind, and they do correlate pretty highly when you look at it over a season for a particular basin. But if you look at it, if you were to do an ACE metric, if you were basically to convert pressure to ACE versus wind to ACE, you would get a very strong. You would get a stronger relationship with a pressure-based ACE landfall metric than you would a wind-based ACE metric. Okay, talking about finding analog years. Yeah, so there's I've used some pattern correlation analysis to find analog years. So basically, I have a variety of different ways of looking for analogs, and it's I would say that's more of an art form than it is necessarily a science. So I have a couple of automated metric ways of doing it. I use pattern correlation analysis. They basically look at the current sea surface temperature patterns and then correlate them with basically correlating each year back to say 1950, do pattern correlations over a basin with the current year. So that's one way I look at it. I also have basically a spreadsheet of various climate indices that I then will give various weights to each climate index and then compare them with what the current values are. One of the challenges that I have is that it's fairly straightforward to find analogs to the current situation. It's a little more challenging from a automated perspective to find analogs to a forecast situation. I suppose I could also do pattern correlations between, say, forecasts from like the North American multi-model ensemble. Doing that, basically taking forecasts of what the large scale the model's ensemble says it's going to look like, and then pattern correlating observations with that. I think that's something I'm going to probably try to look at here in the future. Okay, so yeah, so the next question is, what about the statistical model? Is it just multiple linear regression? Are there any probabilistic approaches? Right now, it is just multiple linear regression. I think in the future, I do want to try some alternative approaches. I know I've worked with some others, and we've tried various like machine learning approaches and things, and often it comes out fairly similar to just using simple multiple linear regression. The challenge is that some of these relationships I think are pretty linear, so linear regression works fine, but I think if you dial down and look at things, especially things like El Nino, it's not always linear. Recently, it appears that the relationship between ENSO and Atlantic ACE or Atlantic hurricane activity has been more linear, but if you go back into the 50s, 60s, 70s, it wasn't quite as linear. It was basically almost an on-off switch whereby if you had a moderate or strong El Nino, it was very quiet, and otherwise the relationship was fairly mixed. And if you go back to Bill Gray's original seasonal forecast paper in 1984, he did a really pure, just basically pure empirical analysis, and his model was very, very simple. But basically what he would do is he forecasts, I believe it was 6 hurricanes, was his kind of his, climatology forecast. And then he would, I believe, subtract 2 hurricanes if it was a moderate or strong El Nino. And that was it. If it was a La Nina, he did not increase the forecast at all. And I think that's because the relationship back then wasn't as linear as it has been recently. So I think there certainly is more that can be done when you do these kinds of models. I know if you go to that Seasonal Hurricane Predictions website, there are a variety of different approaches being used. I believe some are using neural networks and some more complicated statistical methods. And then we also have some dynamical models, which are basically counting the vortices that spin up in the model and using that as their forecast. And so if actually counting vortices as opposed to kind of looking at how the large scale interacts and how that generally drives it. One thing we have found is that just doing a little bit of comparison with the Glossy 5 model, if you count the vortices out of the model and do an ACE forecast and a hurricane number forecast from that, and you do a statistical dynamical model where you basically take the Glossy 5's forecast at a large scale and take how that typically relates to hurricanes, you actually end up with a very similar correlations. So basically meaning if the model has a more conducive environment, it spins up more vortices. So the model is correctly physically representing the hurricane activity. All right, any other questions? All right, well, thanks again for having me. I hope all of you continue to stay safe and healthy, and have a great rest of your day. Thank you.